Thank you very much. Thank you guys for coming. I know it's early in the week and that it's good to take the time out. As we've said, I'm Dr. Matthew Leeke. I'm from the University of Warwick's Computer Science Department. Most of my work, most of my background is actually in dependable software, so how you go about designing systems that are in some way robust and resilient and you can depend on the services that they provide. That really led me to machine learning and how we can go and use machine learning to think about dependable systems. But maybe as an offshoot of that, just an interest that I've maintained and has steadily grown to something that I'm now intensely interested in is privacy and the idea of, in particular, context privacy. The main application domain that I've experienced and I've worked in for context privacy is wireless sensor networks. Now, most of you, if I say wireless sensor network, might have some idea of what that means. In general, one of the things that we try to do in our work is to try and think about them in very broad terms so that we're able to take what we develop, what we create, what we come up with, and then go and apply it to different scenarios. Now, you can see here that we have an example of a sensor network, and essentially the nicest way to think about this is maybe to think just of it as nodes, you know, a set of these things over here, these little dots that are scattered somewhere. It may look like this, it may be a grid, it may be less structured, it may have a different topology, but fundamentally we're thinking about devices that have some computational ability, that can do some computation for you, but maybe most importantly, that can communicate with each other, that are able to broadcast messages, and through this wireless interface that I'm claiming they have, every device operates in a broadcast medium. And that's really because it's sort of often confused, I think, with things like ad hoc networking, and you can think of this as a little bit ad hoc in the sense that every device is operating independently using these sensors that it has and then broadcasting, relaying information. And typically, for most scenarios, we think about devices as broadcasting information back to a sink. So intermediate nodes will relay information so that, for example, in the situation of let's take animal conservation, if we have an endangered species that's detected through whatever sensor we have in some geographical space, that information, that sensed information, can be relayed through the sensor network back to some base station. And maybe the thing I like most about wireless sensor networks is that they're an enabling technology. They're a technology that can be applied in all kinds of domains, and maybe the most exciting, certainly one of the most talked about in recent years, has been the Internet of Things. And this idea that the devices that you have in your home, not necessarily the things that currently have a wireless interface or currently are networked, will soon be networked. Those devices will soon be not just internet enabled, but will be interacting with each other and be able to talk to each other to enhance the services they provide you. So you can, we like to joke, I guess, with my colleagues about having your kettle talk to your fridge to work out whether there's enough filtered water to go and fill it up the next time you want a cup of tea. Your fridge deciding whether to order more beer, of course, if you're so inclined, to make sure that you've got some beverages when you get home from that long day at the office. And all these devices will work together as a cohesive whole, each one acting sort of like a sensor, each one relaying information, each one trying to communicate in some way to make your life better. And the interesting thing, and the reason I like the Internet of Things right now to think about context privacy, is really because lots of what we've learned over the past 10, 15 years in wireless sensor networks can actually be brought, adapted, admittedly, and applied to IoT. And IoT really, for me, needs to build confidence. It needs to build the confidence of its users before it can be widely adopted. I'm never going to trust any device in my house to go and broadcast information about my life before it's gained my trust. And of course, that's important, both for IoT and us and our everyday privacy. And when we think about privacy, and again, coming back to wireless sensor networks, we really think about privacy in wireless sensor networks along two dimensions. We think about content privacy and we think about context privacy. Now, I'm very interested in content privacy, but for me, I think the biggest thing is that problem isn't solved, but has largely been addressed to the satisfaction of most everyday users by cryptographic methods. So very often we're able to model nodes in wireless sensor networks using a Byzantine node using Byzantine node modeling, and then to use cryptographic techniques to address the content concerns. When it comes to context, things are a bit different, of course. Now, context, as you might suspect, is a multi-attribute concept. It incorporates things like location, which is the one I'm going to focus on in just a moment, but also chronology, it incorporates time, it incorporates presence. And really, this makes it more of a challenge in my eyes to address in the context of getting from a wireless sensor network to deployment in an IoT context. When it comes to context in wireless sensor networks, maybe one of the most studied areas is that of location. So to think about if you have this huge, say, grid of sensors deployed somewhere, say that endangered animal situation, one of those sensors detects that animal. Of course, that is meaningful. That gives you a location for something that is an asset. And indeed, when it comes to thinking about location, it's actually important in pretty much every deployment scenario, but particularly when it comes to asset monitoring. So if you have, say, an animal that you're trying to protect, or you have soldiers on reconnaissance, or you have your healthcare data making its way across a city, for example, its location at any point in time is telling, and it tells you something about what's happening in that real location. Now, when it comes to sort of how a wireless sensor network would operate, as we've said, an animal would be sensed, for example, or some military personnel would be sensed, that data would be relayed. And of course, provided there are no malicious people in the world, or no attackers who want to circumvent that particular process, everything's fine. But of course, we know that there are attackers. We know that there are malicious people in the world. So then it leads to the question, what's the worst case? Well, if you think about the simple model that we have, an animal being sensed in some geographical region, an endangered animal setting off a particular sensor, is a problem, because that's information that is then going to be communicated, potentially over a large area, potentially a poacher somewhere in between that area and the base station it's being relayed to will want to go and get that endangered animal. And actually, in the original formulation of the source location privacy problem, this problem of maintaining the privacy of a particular location of a sensor, that's the way it was framed. It was framed as the panda hunter problem. And this is kind of important for lots of different reasons, not least because when we translate this kind of model of wireless sensor networks and this kind of problem of source location privacy to IoT, things get very real very quickly for a whole lot of people. When you think about cities, when you think about wireless sensor networks being used as critical infrastructure to improve things like urban mobility or to improve the communication of healthcare data, you end up in situations where people's lives can be exposed. And I guess an important consideration is to think about those attackers, to think about what they would want to do, because it's not just, of course, hunters, it's not just pandas, it's my healthcare data, how many beers I'm ordering from Amazon, or potentially. There's the strength of an attacker, and I guess a lot of work was done when this problem was first proposed, but kind of 3 years after the original proposal of source location privacy as a very important problem to tackle for wireless sensor networks, the strength of an attacker was shown to be characterized by two things, by presence and by actions. And that roughly translates to what an attacker can observe, what they can see, and what they can go and do with that information. For the most part, the work that I've done for the best part of a decade now focuses on distributed eavesdroppers, and the idea that we have this attacker who can see the network, it can see the whole network, kind of has this global knowledge, but doesn't have a global presence. It can see portions of the network, it knows about multiple locations, but can't necessarily see the extent of the network. It's important to note that the attacker moves in response to broadcast observations, because that's the thing that would trigger a response, of course. If it can find some information, it can act upon that information, and it will do that through movement. And the assumption being, sort of under this model, we would try to think about situations where an attacker getting to the asset that we're trying to monitor, be it an endangered animal, be it military personnel, that them even arriving at that situation or getting close to would be a problem for us, of course. So under this model of wireless sensor networks, where we're trying to deploy lots and lots of sensors, we're trying to monitor some asset like an endangered animal, we're then trying to think about how an attacker might behave or what they can respond to. How do we go about making sure that an attacker can never find or never locate our asset? Well, the fake source approach was proposed at roughly the same time as sort of source location privacy really gained traction, I think, in the literature. Lots of nodes, essentially, under this idea of using fake sources to dissuade an attacker. Essentially, what we're saying is loads of devices will act as fake sources. So they will essentially pretend to be a source, pretend to be that source that has detected that asset. And by doing this, we will hopefully pull an attacker in the wrong direction. Now, that's a very simple explanation of what very rapidly in unstructured networks becomes a very difficult problem to solve. When it comes to showing the extent of the performance of just using fake sources to try and dissuade attackers from finding our assets, it turns out that you can achieve very good privacy if you're very happy to expend a lot of energy. If every source in the network was if every node, I should say, in the network was very happy to act as a source, of course, it would be each would be indistinguishable from the next, provided we assume that we can't go and decrypt. We have strong encryption, we can't go and decrypt the contents of each message. It would be almost impossible for an attacker to, with any degree of certainty, ascertain a route back to a source. And of course, or a real source at the very least. It's not really practical though, of course, because if we have hundreds, thousands, tens of thousands, hundreds of thousands of nodes, that rapidly becomes a problem that uses too much energy. That solution just doesn't work. So the real question when it comes to the fake source approach is, which nodes should we use as fake sources? Which nodes should be acting as these decoys to try and dissuade attackers? And over a number of years, we've had several results in this area that have been kind of useful in taking fake sources as an approach and moving it towards something that is more practical. When it was originally developed, I think it's quite fair to say that the authors come out originally noted quite poor performance in both energy and actually achievable privacy under the models that they had. In recent years, there's been a lot of work, not just by ourselves at Warwick, but right across the UK, not just in source location privacy, but in sensor technology that obviously informs what we go and do and what we go and model. One of the first things we wanted to address when we sort of arrived at this problem was the idea of energy. Because when it comes to sensor networks, batteries, energy, whether energy can be harvested in a particular situation through things like solar cells, etc. It's very situation specific, but regardless of a deployment scenario, you can always be sure that you would like to use less energy. And that's really the goal. So when we set out with that goal, what we're doing is saying that extreme of every node acting as a decoy is something we don't want to do. We want to avoid that. But what can we do that's not that extreme? What can we do as a minimum to make sure that we provide a good level of privacy? And what we did is to develop algorithms that essentially strike a balance between the amount of energy expended by a network, which will hopefully maximize that network's lifetime, and the privacy afforded. Essentially what we did is we showed that under some situations, if you have a single attacker that has this sort of this distributed eavesdropper view of your network, you can actually get near perfect privacy in some scenarios. If you have a stronger attacker model, or you have indeed multiple attackers, that algorithm actually kind of falls down a little bit for various reasons that we went on to address. Probably building on that, we sort of moved on to say, well, let's understand this problem in more depth. What can we do to really get to the heart of this problem? By formalizing it, mathematically speaking, we managed to prove formally that the problem is NP complete. Now, it's not, for those of you who are not computer scientists, it's not crucial right now to understand and go and look at what NP completeness means. But in terms of this problem, it means that it's very easy, if you were to show me a suggestion for which nodes you'd like to pick to act as fake sources at any point in time, it's very easy for me to say, yeah, that's a good idea, or in fact, no, that's not a good idea. But in terms of coming up with a good, or even an optimal, if that should exist, solution for which of these nodes we should pick, it's actually very hard. And it's going to be a real problem for us. And most sort of, I guess people like me, people who are concerned with building systems, when they encounter one of these problems that they can show to be NP complete, our sort of knee-jerk response, of course, is to come up with a heuristic, is to come up with a way to come up with a solution that may not be perfect, but actually is probably good enough for most scenarios. So what we went away and did is to think about how we can do that. And that really led us to look at things like broadcasts and how often nodes broadcast. You know, if in order to relay that information, you need to broadcast at, say, 2 messages per second, what kind of broadcast rate do these fake sources need to have in order to dissuade attackers? Moreover, if we have collisions in our network, what's that going to do? What if not every message is going to get through? How can we guarantee certain levels of privacy under those? And we were able to characterize the impact of broadcast rates, to think about what collisions do. And this heuristic algorithm really informed what we've done since. I mentioned having the idea of multiple attackers, but of course, if we're going to take wireless sensor networks and we're going to get it sort of out of this this domain of thinking about the panther-hunter problem, and we're going to bring that to IoT, and we're going to start to think about many interacting devices, but not wanting to expose the ins and outs of a user's life through that network, we need to think about multiple sources, because of course multiple devices kind of implies multiple sources. More recently, we've looked at the idea of having multiple sources, even with very simple models like the ones I'm doing here, where you can see sort of the yellow representing sinks and the green representing sources. Even where you have these, and they're very simple, you rapidly run into some quite interesting results. One of the most notable in a recent paper that's going to be presenting in a couple of weeks, I think, is that actually if you have these multiple sources and you have a network that is either sufficiently small or sufficiently large, it turns out that if you have a privacy preserving algorithm, so if you take the work that we've done and you take that algorithm and you run it on that network and say, go and protect it, actually, sometimes it's worse than just not doing that at all. And that's a concern, of course, because that means that at some level, we might want to fundamentally reconsider how we deal with each of these. We might want to rethink this idea of having a single sort of monolithic algorithm that goes ahead and tries to preempt what an attacker can do. There is probably something smarter we can do to get the kind of emergent behavior for each of these that we would like. And of course, that represents an area of future work, knowing that we've got to prove that actually our algorithms sort of break in some contexts. These are the kind of results that back that up, and hopefully if you're very interested in this, you'll hopefully go and read that paper. We're really pleased. I should sort of mention my collaborators, Arshad Jumka, Matthew Bradbury and Joanna Leeke in here, because they contributed to this result, and really it's opened up some new ideas for us about how we might go back to the drawing board, which is often viewed as a very negative thing to be doing, but in this case I think is very exciting. Probably in more recent work, we've looked at how we can take these sort of energy privacy balancing algorithms and develop an algorithm that for a single attacker or for a small number of attackers is able to adapt, is able to produce sort of its own, or estimate I should say, its own runtime parameters. So that regardless of which situation you go and put me in, whether that's the panther-hunter game with thousands of nodes, whether that's the IoT situation with hundreds, it can still work, it can still do something of use. Now, this algorithm sort of was developed in stages. Originally, we set out to sort of just develop an algorithm that could predict its own, or develop its own runtime parameters. It could estimate those at runtime. We then augmented that to use less energy, because we found that predicting those particular parameters meant that algorithm would produce not the best energy utilization for the network. Eventually, we demonstrated that this augmented algorithm was able to produce essentially a solution that used less energy and provided nearly the same level of privacy. And of course, we've spent a number of years working on each of those results, but there's still a lot of work to do here. And what excites me, I think, the most is that when it comes to thinking about wireless sensor networks, we've got a long way to go, and there's even further to go when it comes to bringing that knowledge to IoT in its various forms. We want to think about topology. We want to think about particularly unstructured topologies, or situations that can arise in real deployment scenarios where one node becomes isolated or something breaks. So we want to bring some of that dependability in. We want to think about having multiple sources at scale. The experiments I showed you where we have those kind of interesting results hold for networks of hundreds of nodes. They hold for small numbers of thousands. I don't know what happens if you go and put 200,000 nodes into that situation. I genuinely don't, and I'd be interested to know. We want to think about real-world deployments, because of course it's one thing to prove that a problem is NP complete. It is one thing to go and simulate that. It is one thing to do small-scale deployment. But being able to take our ideas and test them at the biggest possible scale is exciting, because hopefully they break and we can learn something from that. Maybe they'll work and we can go and hopefully make use of them in a real-world scenario. We want to think about lots of the good work, and it's going on throughout the UK, various universities and institutions, that's going on in energy harvesting sensors. So our big concern has been reducing energy utilisation. If you know that your sensors can recover energy, actually that there is a symbiotic relationship there that you can exploit. If you can recover energy better than I can use it in some sense, then there's no problem. So maybe there is this sort of level at which energy utilisation is okay, and actually then we've seen that we can improve privacy by using that. I suspect it's never going to be the situation that we can just use every node in a network, and for that reason, when it comes to moving between what we've understood in the context of wireless sensor networks, when it comes to taking context privacy for something that we've sensed, be it on a small scale, be it on a large scale, there's lots of knowledge that we're going to bring to IoT. There's lots of it that won't quickly map. There's lots of it that just won't work. But I think that relationship is important. If, as a technology, wireless sensor networks is touted as being a sort of underpinning fabric of IoT, we want to try and work out, with that as a starting point, what can we go forward and do? And I suppose that's really my goal. And one of the things that I hope to do at the Institute is to be thinking about these ideas around sort of the privacy of individuals, the privacy of if you're in your home and every device is talking to each other, and I'm stood outside your home with a laptop and something that's got a Wi-Fi receiver or whatever network receiver I require, what can I conclude about you, and how can you prevent me concluding that? Okay, so that's just a few acknowledgements to the people I've worked with and the various authors who contribute to the problem. I'd be very happy to take any questions.